You don't need it. Okay, so just need it.
All right, so what I'd like to do is spend a little time talking about the memristor from our point of view within my research group at Hewlett-Packard. For many of you, you're going to have seen a lot of this material before, and I'm going to keep presenting this material until people start understanding it, okay? It's clear that for the most part, people haven't quite grokked on this concept yet, and so we're going to have to get one of these strange attractors going and get some associative memory. And hopefully I can convince you that this is not just something fun. This is going to change the way we do electronics, fundamentally. All right? Now, the people who have been participating in the research work in my laboratory in this general area, we've been working sort of in the general area of nano and nonlinear electronics for about 12 years now. And if I try to count up the total number of people, both who have worked directly in my laboratory, collaborators within HP, and our collaborators in various national laboratories and universities over the years, it exceeds about 250 people. So it has been a long process, and if you know what's happening now, it's actually picking up. It's going faster and faster and spreading wider and wider. So this is an area in which, as you'll see, I'll make some predictions toward the end of my talk, and if that doesn't wake you up, nothing will. All right, so outline of my presentation. I will give a little bit of a presentation of what is a memristor, at least from the physical point of view. And most importantly, what is a state variable? That's really the key issue here. Memristors are dynamical devices. They're not your old standby device that you've ever worked with before. They have state, and that really distinguishes them from anything and everything else. They're latches, if you will. Think of a memristor as a latch, and even something more interesting, it's an analog latch. So what is the mechanism for bipolar switching? I'll talk about that. Why is a memristor a nanoscale device? Why in an electronic system in which we care about voltages of about a volt or so, why is it necessary for memristors to be at the nanometer scale? Why is it so hard to make a discrete memristor, for instance? People are bombarding me with requests to send them discrete memristors that they can plug into their breadboards and demonstrate them to their students. And we say, sorry, it just doesn't work that way. If we were to send you a packaged set of nanoscale memristors, the first time your students touch them, the electrical discharge would blow them all up anyway. So there is a little bit of a problem there. It's very hard to make discrete memristors. I'll talk something about retention and switching speed, because most of what I'll talk about will be thinking about memristors as binary elements in a memory system, but I'll get off that topic a little bit toward the end. And then Dimitri's already talked about it, but I'll sort of review it a little bit about this issue of stacking 3D. And how many libraries of Congress could you put on a 1 square centimeter chip using this process? And the answer is going to be a little bit astounding. If you actually hear me say it and don't believe me, or actually and don't question me, at the end there will be something wrong. Okay, so prediction of a new circuit element. We have had 3 fundamental passive devices for a little over 150 years. And then all of a sudden, in 1971, while he was examining this whole issue of placing nonlinear circuit theory on a firm mathematical foundation, Leon predicts the existence of a new fundamental device. Absolutely astounding in an era where, as then and even now, as mature as electrical engineering is to come up with a fundamental new element. I literally put this on the same level as the prediction of the positron by Paul Dirac when he generalized the equations of quantum mechanics and made them relativistically covariant, and essentially went from a linear to a nonlinear type of a mathematical foundation. That's exactly what Leon Chua did with respect to our electronic circuits. And he did more than that. He did more than just predict the existence of the memristor. He described its properties. And then a few years later, our chairman of the conference here, Steve Kang, came along and generalized the concept and essentially went from an integral formulation, which is here, to a differential formulation, which is actually more important, really, because what it does is it exposes the physics of the devices. It allows you to understand how these devices actually do work with respect to their physics, but also it provides the means by which you can create models that are useful for simulation. You can make a SPICE model with this, and you can put it in your simulator, and you can understand how circuits are going to operate using this differential formulation. And there's something that you should note about it, and that is it requires two equations. All right? Because memristors, as were so eloquently stated by actually Steve Kang, are dynamical devices, and therefore they have an explicit time dependence that you must account for when you are looking at how the devices work. So you require an equation which describes the essentially instantaneous conductance of the device, if you will. What is the relationship between current and voltage at any given point in time? But then the resistance of the device, if you will, is explicitly a function of a state variable, some internal variable which describes the state of the device, and it also can be a function of current or whatever else. And then the state variable itself winds up being a function of the state variable, or the time derivative of the state variable winds up being a function of the state variable, and it can be other things as well. So without these two equations, without understanding what these two equations are, you can't do anything with your memristor. You can't characterize your device. And so if you have a memristor and you wish to understand what its devices are, you must figure out this equation. You must understand what W, what the state variable is as a function of time. And once you have that, you can predict every property that you need to know about the device. So, what's the deal? Well, the deal is, as Leon said, the memristor has a pinched hysteresis loop. All right, whatever that means. Well, what it means is that the device cannot store either charge or energy, but it does store information. And that's sort of the interesting issue about this. And this is also why, in principle, a memristor can be non-volatile. Why it can store information effectively forever, because it doesn't have either energy or charge in it to bleed away, to dissipate with time. All right? So if you look at the current voltage plots for the four sort of central fundamental elements, resistor, I mean, people are always asking, well, where does the diode fit on this? Well, the diode fits here. I mean, within this concept of nonlinear devices, a diode is nothing other than a nonlinear resistor. So anything that has some sort of a curve that is not hysteretic in the current voltage, that's a resistor. Okay, it falls there. Capacitance and inductance look the same in some sense. The reason they're different is because they're 180 degrees out of phase with respect to each other. And then, of course, the memristor has this interesting pinched hysteresis loop, which can only be described based on this idea of the state variable and how the state variable varies in time. So that's the family. Now, it turns out that people have been making memristors unintentionally for many decades. I mean, there are actually papers from the 1960s in which people had made memristors, but they just simply didn't connect the issue or the idea of the pinched hysteresis loop that they were measuring experimentally, obviously they'd never bothered to read Leon's papers, right? We were among those. We were also making devices, unintentional memristors, and they sort of looked like this. They were devices which had a bottom electrode, a central material, in this case an oxide of titanium, and an upper electrode. They sort of look like a capacitor. Sort of looks like some device, a leaky capacitor or something like that. And we and everybody else puzzled for a very long time over what the heck this thing was doing. How do you even characterize these devices? I mean, we would try to look at them because what we saw was that they were switching in some fashion. But what is that switching a function of? Is it a function of voltage? Is it a function of current? Is it a function of power? Well, the answer is none of those. It's a function of charge. Whoa. I mean, where does that come from? So it turns out that the key issue here is that this material that we were using and many other people use in the device is a semiconductor. And so it turns out that a memristor is a semiconductor device. Now, where memristorance comes from in this titanium dioxide material is the fact that, first of all, titanium dioxide is a wide bandgap semiconductor, has a bandgap of a little bit over 3 electron volts, and it is auto-doped. In other words, if you remove some of the oxygen atoms from the lattice of the titanium dioxide, the remaining vacancies are essentially positively charged donors to the material. And in fact, you can remove up to 3% of the oxygen from the lattice without actually causing the basic structure of the material to collapse. And if you think about that, what you then have is actually a metal. You have something with such a high doping that it's really metallic in its nature. So you've got a material here in which it's possible to go through effectively a metal insulator transition by adding or removing vacancies from the system. These vacancies can diffuse in the material, but depending upon whether it's a single crystal or polycrystalline material, the diffusion of those vacancies is really very slow. So what we finally understood that we had after many years of going down blind alleys and just sort of banging our heads up against the wall, were devices which in fact had a binary layer or a two-layer system of titanium dioxide. Our devices, because of the processing that we were doing to improve switching properties, contained actually two different layers of titanium dioxide. One was a stoichiometric layer, essentially this 3eV bandgap material, which is very insulating. And the other was a oxygen-deficient material, which is highly conductive. And so we had 2 layers of titanium dioxide in the devices, and what we could see by essentially running current voltage characteristics is this type of a pinched hysteresis loop here. And for this particular sample, it turns out that the interfaces were fairly clean. And so one of the interfaces here is a metal semiconductor interface. So we have a Schottky barrier there. And so you can see the Schottky barrier right here in this part of the IV curve. What you see is that the off state, if you will, or the high resistance state of the device is actually a diode, or at least a rectifying contact, Schottky barrier. And then essentially what we do is we somehow turn that Schottky barrier into a fairly thin tunnel barrier. So we're going back and forth between 2 end states, but in fact the switching itself is continuous. This is not a binary switching event, it's a continuous switching event. And we can stop the process at any point in time and have any intermediate state between a fairly low resistance, thin barrier tunnel region and a Schottky barrier. The resistance change if you want to measure resistance at low voltage, the resistance change typically for us is about 3 orders of magnitude. But that's just convenient. It can be as high as 6 orders of magnitude easily. Turns out that that's not necessary, but you can make this resistance change effectively as large as you wish, if what you want is some sort of a binary switch. So it was finally Greg Snyder in my lab who pointed out the fact that although this doesn't look like the pretty type of pinched hysteresis loop that Leon was showing and others early on, it was indeed a pinched hysteresis loop, and therefore this should have something to do with memristance. And so I came up with a very simple model to explain how this system could be a memristor. And this simple model, essentially, I'm going to present it in two layers. The first layer is going to be at the freshman level, shall we say, and then I'll try to step it up a little bit. So the simplest idea was that we knew from our physical measurements that we had 2 different layers of titanium dioxide in the system, one stoichiometric and one oxygen deficient. Well, those oxygen vacancies will drift when we put a high enough electric field across the device. And so that's what's happening here. If I put a positive bias voltage here, that will cause the oxygen vacancies to drift to the left. But what that does is it makes this region here of stoichiometric titanium dioxide more narrow. Now note, we are not creating or destroying oxygen vacancies in this process. We're simply redistributing them in the system. If we then put a plus voltage here, we can draw, a minus voltage here, we can draw the oxygen vacancies back. And so the switching, in effect, is just moving oxygen vacancies back and forth through this material and changing the resistance of the stack. Now this is actually a fairly simple type of mechanism, and so you can immediately start thinking of a large range of systems that will do something similar. Silver and silicon. Practically any oxide with vacancies in it. Chalcogenides. So there are literally hundreds of papers that have been published over the past 50 years in which people observed memristance but didn't understand what it was, and so they would call it things like anomalous capacitance or anomalous this or anomalous that. And so anytime you see a paper with a title anomalous, or the word anomalous in the title of a paper, you know there's probably something wrong in that paper. And so that's really what was going on. If people had sort of just thought about it for a minute, they would have realized that if it really is a capacitor, you don't have a pinched hysteresis loop, right? Your current voltage curve doesn't go through 0. It goes through something else. So all of these effects, all of these explanations for the effects that people had over 40 years were essentially all wrong. What the explanation behind this effect is it's memristance, and the simple mechanism that I just explained to you, essentially drift of these charged dopants in the material, can be written in a very simple equivalent circuit. I'm originally a chemist, and so this is probably the most complex equivalent circuit that I can write down. But what it is, it's 2 variable resistors in series with each other, one of which has a high resistance, the other of which has a low resistance. And effectively what we're doing by applying a voltage across this system is we have a field inside that's causing the dopants in the semiconductor to drift to one side or the other. So that's really what this shows. And now we have 2 equations. I've got an equation which describes the current voltage characteristic, or the instantaneous quasi-static current voltage relationship at any point in time, depending upon where the dividing line is between the stoichiometric and non-stoichiometric material. And then I have another equation which tells me what the drift velocity is. So dW by dt in this is the drift velocity of the vacancies, if you will, at the leading edge of this dividing line between doped and undoped material. And so I've got the mobility of the vacancies times the electric field described in a little bit different way. And what you see is these two equations here are exactly the equations for a memristor. So this essentially, showed that one way, anyway, of achieving memristance in a circuit is to have a system in which both atomic and electronic degrees of freedom are coupled and are time dependent under the application of an external voltage or a field. The memristance of the device is actually, once you have these two equations, it's easy to figure out what the memristance is. And so what you find out is that the memristance looks like this. And for this very simple model in which we're talking about linear drift, essentially ohmic drift of the ions, and I'm just assuming that the current conduction here is ohmic, you wind up with a factor of 1 over d squared, the width of the device in the memristance. And what that tells you is that memristance is 1 million times larger at the nanometer scale than it is at the micron scale for a simple system like this. And that's one of the reasons why it's so hard to find. It's been so hard to figure out. We've really only have memristance when we're at nanometer scale. And so what's happening? Well, now practically all of our electronic devices are at the nanometer scale. And if you start reading papers about what people are observing in their electronic circuits, what are they seeing? They're seeing all sorts of anomalous capacitance or anomalous inductance. They're seeing all sorts of hysteresis in their circuits that they weren't expecting. And what is it? It's memristance. They've got high voltages, they've got high fields, small distances, the atoms are starting to move. And so memristance is essentially cropping up all over in all of our electronic circuits. One thing is to be aware of that and to try to compensate for it. But of course, the other issue is let's use it as a feature. Let's start building circuits with intentional memristors in them. But first, we need to understand this process or these memristors a lot better. So instead of having this fundamental freshman level of idea of drift and diffusion, let's sort of generalize now the types of behaviors that people use when they want to understand semiconductor devices and look at the Poisson equation and at drift and diffusion for electrons and holes. But now, instead of assuming that the dopants in the semiconductor are static, we now have to put in the drift and diffusion of the dopants as well. So now electrons, holes, and ions are all coupled by the Poisson equation, and everything's moving at the same time, right? And you have to keep track of all of that. And when you do, what you find is that, in fact, this very simple freshman level picture emerges. It comes out because what you see is that instead of just having a sharp dividing line between a region which is oxygen deficient and a region which is stoichiometric, you wind up finding that the effective dopant concentration, if you will, has a very, very steep function with position in the junction. So if we start off with a device in which the, and I've got this is an older version of a slide, sorry, I got two things switched around, that's a problem. But if you start off with a system in which the oxygen vacancies are uniformly distributed throughout the system, that would be an on state. If I put a positive bias voltage here, that's going to drive vacancies in this direction. And so this should say off switching. So that switches the device off. If I reverse the bias voltage, it will move in the other direction. And the issue here is that we find a little interesting piece of physics that didn't exist in that first simple freshman model. And that is, of course, in this particular case, what we're doing is we have drift going in this direction, but we're increasing the concentration here. So diffusion is operating is going in the opposite direction. So we've got a diffusion current going this way, a drift current going in that way. And so what that means is that off switching is actually slow. It's a little bit slower because you have the opposition of drift and diffusion. In this particular case, for on switching, drift and diffusion are going in the same direction, and so that on switching is very much faster. And in fact, you see that in the IV curves, but you can also measure that in systems. And so generally in our devices, if we switch at the same voltage, we see that the switching time for the devices is about 100 times faster for on switching than for off switching. Now, if you want the two devices to switch on and off over the same time period, what that means is you need a larger voltage to do the switching. But it's not 100 times larger voltage because there's a lot of nonlinearities that are going on here. So normally it's maybe a factor of 2 difference in the voltages will cause this switching time for on and off to even out. Now there's another issue, and this was figured out by Dimitri, and actually Dimitri did all of these simulations here as well. But another issue that Dimitri figured out was this issue of the time difference between switching time and state lifetime. In a normal system, you'd normally think about, with using the Einstein-Nernst relationship, you would have at most a factor of about 3 orders of magnitude difference in the switching time and the state lifetime of a system. And that's because the Einstein-Nernst relationship tells you how drift and the mobility and the diffusion constant in a semiconductor are related to each other. However, at very high fields, that Einstein-Nernst relationship, it's not a law, it's only a relationship, it starts to break down. And the reason it breaks down is because the field can become so high that you actually distort the potential well in which the oxygen vacancies are moving. And when you distort that potential well, you can significantly lower the effective activation energy and therefore get effectively an exponential increase in the drift velocity. And so that's what happens. So the drift velocity is actually exponentially dependent on the field. It's not linearly dependent on the field. And that actually turns out to be a really useful thing for switching. Because what that says is that at low fields, the drift velocity is really very small, and so you can have extremely long lifetimes of the state of the device. In other words, if I want to write a 1 in that device, and I want that device to remember that 1 for a long time, that's what this gives you here. But if I want to switch the state in a very short time, I can do that as well. Because we can go to high enough fields in these devices that the drift velocity actually becomes 1 meter per second. So we can go from diffusion velocities, if you will, of nanometers per 1,000 years or less to drift velocities of 1 meter per second. So you can switch the device in roughly a nanosecond, but once you've switched it, that information will stay there for as long as any of us in this room care. Now, one of the things that we've done, and I don't really have enough time to go into this in detail, but there's going to be another talk from one of the people in my group who's going to describe this in more detail. Historically, most of these devices have been made using fairly gross fabrication technologies, and so the areas of the devices were very large. And yet people would make measurements, and they saw that the electrical characteristics of the devices did not scale with the area of the device. And the reason was because, in fact, in these older devices, people had to do what was called a forming step. And the forming step literally created a switching center, okay, which is shown here. We expose this literally by ripping the top electrode off the device, and you wind up seeing that there is some sort of interesting pillar. This material here is titanium dioxide, and that pillar there is an oxide of titanium. And that's where the switching, or at least it's where the switching starts. The story is a little bit more complex. But the issue is that what we wanted to do is we wanted to do a series of electrical tests that would allow us to really understand electrically what was going on and also expose the physics of the device, how everything is actually going on. So the way in which we do that is, again, remember, this is a dynamical device. So all of the measurements that we take on the device must be explicitly time dependent. If you make any measurement on one of these devices in which time is not the independent variable, you are making the wrong measurement. So if you're going to collect an IV characteristic, what you have to do is you have to measure voltage versus time and current versus time, and then you can combine those two measurements to give you an IV characteristic. If you try to take one of these things and put it on a curve tracer, you are in big trouble. Because what's going to happen is the state of this thing is going to be changing in time, and you're going to drive your curve tracer into oscillations. All right? So most of the time when people try to look at these devices, they think that they've got an oscillator, they think they've got something funny going on. What it is, it's the fact that this thing is smarter than the software in their curve tracers. And so they're just driving their curve tracer into an oscillatory type of situation. So you've got to build, I mean, bottom line is you've got to build your own equipment to test these things. Curve tracers don't work. All right? So what do? What you do is you're going to make all your measurements as a function of time. And for instance, you're going to measure current and voltage as a function of time. And the way we do this is in sort of like a two-step process, if you will. We essentially measure the state of the device by collecting an IV characteristic over a range of voltage which does not perturb the device very much. Okay? So we try to do essentially a non-perturbative test of the device state. Then what we do is we apply a voltage, here, 1 volt, over a microsecond period of time in order to push the state, in order to cause the state to evolve. Then we measure the state again. Then we pulse it again at the same voltage. Then we measure it again, we pulse it again, we measure it again. And we do that until we have collected, until the sum of all of these pulse widths adds up to about 30 seconds. Now, since we start off with a microsecond, that could take a very long time to collect all of this data. So in fact, if you notice, these pulses are actually increasing exponentially in time. So that our last pulse is actually a 10-second pulse. Now, we collect both current and voltage data using this. We can take now IV curves. We can take all of this information here, and we can plot a whole bunch of IV curves. I think it's about 440 IV curves that we get out of one of these measurements. Then what we have to do is we have to take that device and we have to set it back to its initial state, and we have to do this again for a different voltage. All right, then we test the device as a function of time for a different bias voltage. Then we have to reset the device back again to its initial state, test it for another voltage, and we have to do that for several voltages in order to be able to look at both, essentially, if you will, the time dependence, which will give us flux or charge dependence, and because these are nonlinear devices, we also need to look at the explicit voltage dependence of what's going on. If you make any other measurement, these devices, this memristance is not a coercive phenomenon. Most people who are out there trying to measure their devices are trying to essentially measure a coercive type of system. They're making measurements as a function of voltage, and they're completely fooling themselves. Have to look at the time dependence. Okay? So what you wind up with is a large number of current voltage characteristics. This is just a very small section of them. And what we can do with these current voltage characteristics is we can actually fit them to an appropriate conduction equation. And in our case, the appropriate conduction equation is the famous Simmons tunneling equation. It fits our data perfectly. And we can essentially do a nested fitting procedure. But what we wind up doing when we do this nested fitting procedure is we fix all of the parameters in the tunneling equation, and we only allow one parameter to vary as we look at all of our different IV characteristics. And that one parameter that we allow to vary is the tunneling width. So in other words, if you think about our model, we've got a model where we have a thin layer of stoichiometric titanium dioxide. What's happening is we are changing the effective thickness of the titanium dioxide, which is changing the width of the tunnel barrier. So the width of the tunnel barrier is our state variable. So when we are changing the state of the device, we're changing the width of the tunnel barrier. And we can see then how only one parameter out of literally 440 different IV curves can give almost perfect fits to all of those 440 IV curves just by varying that one parameter. But now what we've got is the state variable as a function of time, because all of these measurements were done as a function of time. So now what we can do is we can plot for the different voltages. So here is a set of voltages that we used to collect data over. So for a set of voltages, we can look at what the state variable was as a function of time over 7 orders of magnitude in time. We can also numerically differentiate this and get W dot, essentially the derivative of the state variable out. And we can express the derivative of the state variable as a function of the state variable here. This is exactly what Steve Kang's and Leon's equations require. Okay? You need to know the state variable as a function of time. Well, here it is. You need to know the state variable as a function of, actually, of the derivative of the state variable as a function of the state variable, but however you want to phrase this. You have this equation here, and now you know everything there is to know about the device. Everything that you need to know. You can calculate once you've got this. Now, because this thing is determined by drift and diffusion, and you've got this highly nonlinear drift term, there's not a simple analytical form for this. And so what we did is we had to come up with an analytical approximation and then adjust it a little bit. So the equation for fitting these data is a little bit complex. And what you see, it's actually an exponential of an exponential. All right? Now, the reason for that is because we've got nonlinear conduction, we've got tunneling, so the current voltage characteristic is exponential, and we also have exponential drift. The drift velocity is exponentially dependent upon the field. So that winds up giving you an exponential of an exponential. This is tremendously nonlinear, and that's actually very exciting because the more nonlinear a system that you've got, the better it is for computation. And the larger range of time you have accessible to you for this system. So here, now that we've got W dot, as I say, you can calculate any property that you want. You've got W dot, and so you can calculate the off-switching time, as long as you put appropriate voltages. You can calculate what the switching energy is. You can calculate what the state lifetime is. One interesting result is that these data essentially predict that the state lifetime is infinite. In other words, over 7 orders of magnitude, we don't have enough data to predict how long the state lifetime is. So it looks like it diverges literally. So that what that's saying is that the diffusion velocity of these things is really very, very small. So we can calculate all of this, and we can do measurements, and we compare measurements and calculations. And essentially what we see is that for our smallish devices, for devices that we make which are intentionally 50 nanometers or so, we can switch these devices in roughly a nanosecond, a few nanoseconds, and the switching energy is a few picojoules. That's essentially nothing. That's as good as you need to be, just because the circuitry that you connect things up to are going to be slower than that and dissipate more energy than that. All right, so scalability. The devices actually scale in a very interesting fashion. What we always see is that the smaller the device, the better it looks, the better its IV characteristics look. So this is an example of a 5 micrometer by 5 micrometer device, and there is a 50 nanometer by 50 nanometer. And you see that this thing is a lot noisier, a lot less reproducible. As the device gets smaller, it actually gets less noisy, more reproducible. The current scaling isn't there because the larger devices require hotspots, and the smaller devices are smaller than the hotspots of the larger ones, and so you actually start to get good control over what's going on. So I guess I'm just about out of time. So let me just sort of finish here rather quickly, just by saying that these are dynamical devices. These are different from any device that you've ever looked at before. In our titanium dioxide devices, in order to switch the resistance of the device, the low voltage resistance of the device, by a factor of 1,000, we're only changing a tunneling gap by a factor of half a nanometer. So that's what's happening. Our state variable, our tunneling gap, changes by 1/2 a nanometer, and that's enough to change the resistance of the device by 3 orders of magnitude. And we can cause that half nanometer switching to take place in roughly a nanosecond if we apply a roughly few volt bias directly across the gap. Without any voltage, it can take a very long time for this thing to switch. So the switching speed is exponential. The on switching is very fast and easy. Off switching is a bit slower and more difficult, requires a little bit more energy, a little bit more time, or you give it more voltage. And we've actually observed state lifetimes in devices that we made of well over a year. Now we're up to about 5 years on a device. And when we try to extrapolate from our measurements, it essentially diverges. So Dimitri talked about this. Dimitri and I published a paper in Proceedings of the National Academy of Science in December. And so what I suggest you do is go read that paper, because there is no way in a half-hour lecture or in a 1-hour lecture or even in a 3-hour lecture that we can do justice to this idea. It's a really cool idea. And what it says is that with one layer of CMOS, you can control effectively 1,000 layers of memristors almost trivially, if you could make it. I mean, that's the hard part. We actually think that, we're starting to make device sizes now, wires, that are down to 5 nanometers with a 7 nanometer half pitch. And so if you just look at that, just at the wire size that we're making now, that corresponds to half a Library of Congress in 1 square centimeter. All right? Now, with this approach of Dimitri's, we think that we can hit 8 layers. We can make an 8-layer system relatively straightforwardly. All right? So there's already 4 Libraries of Congress on a square centimeter of a device. And the interesting thing is that it does not require any transistors to be smaller than transistors that are being made today. 30 nanometer effectively what we're saying is that transistors do not have to scale any smaller than they are right now. You can stop scaling transistors today, and we could, just by building more and more layers of memristors on top of a transistor system, we can take care of scaling of memory and storage essentially for the next several decades. So, there's all sorts of questions for systems people. But I'm out of time, so I think I should just stop right there, and thank you very much.
So I thank Stan. So we prepared 2 souvenirs, one for you and one for your boss, Banerjee.
Oh, thank you very much.
Who is very supportive. So we will have a 20 minutes coffee break. We will reassume at 11:30. So let's enjoy the break and the good conversation. Thank you.
Thank you.